Geotechnical Engineering Part A, Soil Mechanics Chapter 8, C page. So let's define some definition. Isotropic soil. If the hydraulic conductivity remains the same in different direction inside the soil at any arbitrary point, we can consider that the environment like a isotropic environment. So it means our Kx hydraulic conductivity in x direction should be equal to the hydraulic conductivity in y direction in a 2D environment. So if our Ky is equal to, for example, 5 or 10, Kx should be equal to 10. But for homogeneous soil, we just call that if the hydraulic conductivity remains just constant in any arbitrary point. So for example, if we have K x is equal to, for example, 10 here, ky 10 and kx just like 5 units. We need for example, in point A, we have a ky of 10 unit and kx of 5 unit. We do need to have a ky equal to 10 and again like kx like 5 unit in point B. Just says hydraulic conductivity remains the same, or it remains constant in different points. So for example, ky in both cases are 10 and kx in both cases are kx is like 5, but they are not equal to each other. That's the definition of homogeneous soil. So if we want to wrap it up, one can say, note, any isotropic soil is also a homogeneous soil, but homogeneous soil are not, all the homogeneous are not isotropic. How is that? So it just simply say, if we have isotropic soil, example K is equal K y kx10 ky10, and because this point was an arbitrary point, the same, it should remains the same. So again, ky is 10 here, kx again is here 10. So this is also the isotropic environment is also homogeneous because they are also, can just consider ky independently is constant and kx is also constant. But for homogeneous soil, if this is ky equal to 10 ky kx5 for both points A and B, definitely because kx is not equal to ky, this is not isotropic. So this is a non-isotropic but homogeneous environment, again in 2D, and apply the same concept for a 3D. So again, for an isotropic soil, we can call that if the hydraulic conductivity remains the same in different direction for any arbitrary point, we can call that a isotropic. So if you just jot down the C page equation like kx times d squared h over dx squared plus ky times d squared h over dy squared is goes to 0. Then because it's isotropic kx is equal to ky, you can cancel them off each other. You just are just left with this equation, and that's our C page in 2D isotropic environment. So that's a two-dimensional C page in isotropic soil. Let's put it into recall example. So this example, a 2D C page by traveling a horizontal distance of dx, we have a 15-meter travel in x direction. Velocity at x reduces by a 10 meter per day rate of 10 meter per day. What is the traveling distance in dy? We do know Vy is increasing by 7. So it just assume the solid is isotropic, should be provided in the problem statement. When there is no K provided in problem statement, just assume that the problem is a isotropic because they can easily cancel them out. But I just provide it here to you. So just jot down the seepage equation based off velocity. If you remember, that was d squared h over dx squared plus d squared h over dy squared. Remember that this is, you can also, that's equivalent. This is the equation of 2D seepage in isotropic solid in terms of uh, head of water, and this is based off velocity because we are provided with velocity, so we are interested to solve with the velocity equation. So if just the derivation of velocity in x over dx plus derivation of velocity, change of velocity over dy goes 0, so you can easily have a negative 10 drop by 10 unit over a distance of 15 meters, just gives us a rise of 7 units per a distance to dy. Y is the only traveling distance of dy is what we are looking for. Dy or partial derivation of y are same, so dy is just 10.5 meters. Thank you. Solve more problems.